Imagine we're going to roll a dice 5 times. What is the probability of rolling a 3 twice? What if I asked you for £1, and if you did roll a 3 exactly 2 times, I offered to pay you £10? Am I offering you a fair bet? We're going to find out using the binomial distribution. To qualify as a binomial distribution, the experiment must 1. Have a fixed number of trials, 2. Each trial must have only 2 possible outcomes, which we'll term success and failure, 3. Each trial has the same fixed probability of success, and 4. The trials must be independent of each other. The wager I've offered you qualifies as a binomial distribution, since we're rolling the dice a fixed number of times, 5. To fulfill the second criteria sometimes takes a bit of thinking, and what's crucial is how you frame the experiment. In this case, success is rolling a 3, and failure is not rolling a 3. I've no interest individually in 1, 2, 4, 5 or 6. They're nothing to me. All I describe them as is not 3. The probability of success is the same. Each trial, 1/6 chance of getting the number 3. And each trial is independent, since the outcome of a preceding roll doesn't affect what happens next. Consequently, we can describe the experiment as a binomial distribution, since it fulfills all these qualifying conditions, with 5 trials and 1/6 probability of success. Now we define a random variable x as the number of successful trials in this binomial experiment. And it can of course take the value 0, 1, 2, 3, 4 or 5 for the number of times we are successful and roll a 3. And formally I'll assert that my random variable x follows the binomial distribution I've described. And we're trying to find, in particular, the probability that we have exactly 2 successes. I'm just going to draw your attention to a few things that will help you make sense of the formula that I'll present to you at the end of this video, that you can then use to calculate the probability of a certain number of successes occurring in any binomial experiment. P being the probability of success is fairly self-explanatory, but since there are only ever 2 outcomes, it's very easy to work out the probability of failure, 1 minus P. And since there are a fixed number of trials n, if x is the number of successes, then it follows that n minus x is the number of failures we'll see. So I can work out from this description that since you've told me that the probability of success is 1/6, the probability of failure is 5/6. And in seeking 2 successes, it follows because there are 5 trials, we're going to have 3 failures. So let's carry out the binomial experiment. P is the probability of success, and in terms of our experiment, success is rolling a 3. There's a 1/6 chance of this happening. Now the alternative to success in rolling a 3 is quite simply not getting a 3. You've always got to find a way to frame your experiment in terms of only 2 outcomes. So it follows if success is 1/6 chance, then failure is a 5/6 chance. So let's start rolling dice. Now this is a completely random event, so I'm really hoping I do roll exactly 2 3s in order to demonstrate how we calculate the probability of 2 successes. Our first roll is a 3, just what we wanted. And since this is a success, it has 1/6 probability. Our second roll is not a 3. Remember, the binomial experiment only deals in either success or failure, and the only thing I note about this outcome is that it isn't a success, and so has a 5/6 probability. Our third roll is not a 3. Our fourth roll is not a 3. Success. Our last roll is a 3. So here we have the probability of rolling exactly 2 3s when we roll a dice 5 times. We multiply the probability together to get a total probability of 0.0161 or 1.61%. So at first glance it seems extremely unlikely that you're going to roll 2 3s. Well, you may well have noticed that actually there's more than one way to roll exactly 2 3s. For example, But what's the probability of rolling this combination of dice? Good news, it's the same, since the crucial point to note is that we are still multiplying the probability of 2 successes with 3 failures. In fact, we can write it out in this more compact form. The probability of a successful outcome squared, since we want 2 of them, multiplied by the probability of failure cubed, since we want 3 of them. Now these 2 combinations double my probability to 3.22%. But how many different combinations are there? Well, that's where the aptly named combinations come in. I'm assuming that you're familiar with this, but if we are trying to find the number of different ways we can arrange 2 things in a set of 5, we use this notation and use the NCR button on your calculator. You'll find there are 10 combinations altogether, giving us 10 times 0.0161 for a total probability of 16.1%. I'll finish by adding the notation for combinations to my compact formula below and compare it to the textbook formula. You can see how this formula works. This is the probability of success raised to the power of the number of successes I've specified, 2. It follows that the probability of failure will be 1 minus the probability of success, and the number of failures will always be what's left over from your fixed number of trials after the number of successes. So 5 trials less the 2 successes leaves 3 failures. Finally, we use the combination notation to find the number of ways we can arrange our 2 successes in our fixed number of 5 trials. You should have accepted my wager, since on average, every 6 times you play the game, you win one of these.